Okay, this is an antenna program that I gave a couple of years ago at a few of the clubs in the local area. Now with antennas we have lots of choices. First is, are we going to have a horizontal or vertical antenna? There are dipoles. There are phased arrays or driven arrays such as the ZL Special. There are other arrays such as parasitic arrays. That would be a Yagi antenna. Is the antenna going to be in-fed, center-fed, or off-center fed? Is the antenna going to be for just one band, or is it going to be a multi-band antenna? So there's tons of choices, overwhelming number of choices when you start to think about what kind of antenna are you going to have. And in addition to a lot of choices, there's a lot of opinions. Everyone has his favorite antenna. There's the Carolina Window, a big following. There's the Step IR, the Long John, the Yagi. I'm not sure if it's as popular as it used to be, but there was an antenna called the Hightower. And of course, there's the off-center fed dipole. Many people have a lot of success with the off-center fed dipole. So that's just goes to show there's a lot of opinions, but in general, they all work. Now the question is, how well do they work? What best fits your QTH? Are you getting the best performance? Is it working well enough? What can you do to be louder? And what do I really need? What does not work? And how can I learn more about antennas? Now there's a few things that we need to make sure we understand to do with radio waves and current. RF current in a wire creates a radio wave. A radio wave creates current in a wire. That's like transmitting, you put RF current into a wire to create a radio wave. When you're receiving, a radio wave passes over the wire and causes a current to flow in the wire. And current in a wire caused by a radio wave will radiate another radio wave. That's called re-radiation. Now I want to tell you how you can get information on antennas. There's a lot of books out there. You can talk to experienced amateurs and visit their stations. You can visit a local field day. You can experiment and build antennas. You can model antennas with antenna modeling programs. EasyNet is the one the one that I use. As a result, you can build your own antennas, and you can really learn a lot. It's one of the things in amateur radio that you can still build your own, and you can get great satisfaction out of that. All right, now let's start with books. One of the best sources is the ARRL antenna book. This happens to be the 19th edition that I'm using. Antennas don't change a whole lot from edition to edition. Then the ARRL has a series of books called the Antenna Compendium. I'm not sure how many volumes they have, but I've got 5 or 6 of the Antenna Compendium volumes. There's the radio handbook. Even old radio handbooks such as this have really good antenna information. Some antennas that were used a long time ago probably shouldn't be forgotten. There are textbooks. This is the McGraw-Hill Electrical and Electronic Engineering book. Lots of textbooks that deal with electronics and antennas. This is John Krause's book, Antennas, a typical textbook that we used at Virginia Tech. This is the Yagi Antenna Design book. This was written, I think it was by W2PV. The whole book is dedicated to Yagi antenna design. Extremely interesting book. Now, for those of us interested in 160 and 80 meters, and even 40 meters, ON4UN has a book out called Low Band DXing. There's been several editions. I think this is the 5th edition. It has lots of antenna information, particularly for the low bands. There's DXing on the Edge, The Thrill of 160 Meters, a book by K1ZM. Extremely interesting book, lots of antenna information. You can talk to experienced amateurs and visit their stations. Frequently, you'll find an open house. In particular, every year, W3LPL has an open house, and he takes people around and gives them a tour of his antenna farm. He has quite an amazing, amazing setup with antennas. Really, really big antennas. You can visit a field day. There's always a field day going on in June of every year. All of the clubs go out and set up portable antennas and portable stations in the field. The Williamsburg Area Amateur Radio Club, shown here, is always out in force during the field day. It's the last weekend in June every year. And from then on, you can experiment and build antennas. It doesn't take a whole lot of talent to build an antenna. You do need to know how to solder. That's a big help. There's things called a buddy pole that we set up for some QRP operation every so often. It doesn't take much to make a contact. I've even put up 135-foot high antennas held up by weather balloons. Here's a picture from the 70s. We used it in 160 contests and did quite well. You can go to the beach. You can set up a makeshift antenna. This was I think it was a Hustler Mobile antenna on a little stand. And took a QRP radio, a couple of us, and had a lot of fun. Doesn't take a big location to have antennas. This was at a location I had where antennas were severely restricted. These are inverted V antennas and almost invisible. This was tuning my my tower for 160 contest. This was a great antenna right on the edge of the water. We did quite well in 1973 with that. There's a lot of equipment nowadays that's a lot smaller than what I use. This is MFJ 259 antenna analyzer. A great little piece of equipment, and there's a lot of stuff like that out there. This shows the frequency and resistance and the reactance to an antenna that I was working on. And you can model antennas with EasyNet before you build them, or you can do it after you build them. EasyNet is a free antenna program. It's a little bit limited in the free version, but it's quite usable. No, you can't model a big elaborate antenna with the free version, but you can do dipoles and Yagis and inverted V's. The demo is free. It'll do a 2-element quad. The full version is well worth it for $89 if you're going to do a lot of antenna modeling. Now, there's no one perfect antenna for everything. That's impossible. You have to decide what do you want to do, and you need the right antenna for the distance. You also need the right antenna at the right height, and you can be too high. Frequently, antennas are a compromise, particularly for general amateur radio operations. Now, a little bit about antenna fundamentals. A balanced antenna is one where the currents are equal and opposite at the feed point. Now, this would be your typical center-fed antenna. Unbalanced antenna is one where the currents are not equal. This would be such as an off-center fed antenna. And impedance, the impedance of an antenna is simply the ratio of the voltage to current, usually at the feed point or any place on the antenna you can measure an impedance. And the impedance is simply, again, the ratio of voltage to current. At any point where you have a current and a voltage, there is a corresponding impedance. And that impedance is simply the ratio of voltage to current. The feed point impedance is the ratio of voltage to current at the feed point. Now, there's some characteristics to consider for all antennas. There's gain, which is essentially directivity. There's the polarization, or whether the electric field is vertical or horizontal. There's the radiation angle or radiation angles. There's the feed point impedance, very important to be able to get your power into the antenna. And there is the radiation resistance. Now I'll try to briefly touch on each one of these characteristics. The gain in dB versus transmitter power. A gain of 10 dB is equivalent to going from 100 watts to 1,000 watts output with your transmitter. A gain of 3 dB is like going from 100 watts to 200 watts. And antenna gain works both transmitting and receiving. Increasing your transmitter power by 5 dB does not help you hear better. But increasing your antenna gain 5 dB does help you both be heard better and also to hear better. Now let's talk about the gain of a dipole. The gain of a dipole in free space is 2.1 dBi. I'm sure everybody's heard the gain of a dipole is 2.1 dB. Well, it's 2.1 dBi in free space. The gain of a dipole is off the sides and not off the ends. It's off the broadside. The gain in one direction is always at the expense of gain in another direction. Now let's note that the gain of a dipole on Earth, a real dipole, is not 2.1 dBi. The gain of a real dipole on Earth that you might actually put up yourself is 7.5 dBi. So let's remember, the gain of a real dipole is 7.5 dBi, not 2.1 dB. Now, I suggest comparing any antenna that you may consider to a half-wave dipole over real ground. If the antenna that you're considering does not have much more than 7.5 dBi gain, then you may as well use a dipole. A dipole is not a bad antenna when it's up in the air fairly high. And beware of any antenna gain that is given simply in dB. The dB must be referenced to something. Now, I think it's always a good idea to reference antennas to dBi. If you always go back and figure the gain of an antenna in dBi, then you're comparing apples to apples. I could build an antenna and advertise it to have 20 dB of gain. Well, that 20 dB of gain could be in reference to a coat hanger that I'm tuning up with my L-Network antenna tuner. and you buy that 20 dB gain antenna and you can't get out of your own backyard with it, the 20 dB actually means nothing. That coat hanger may have a minus 100 dBi gain, but it's I like to say you can compare it to a wet noodle, and you've got a lot of gain compared to loading up a wet noodle. So remember, beware of any antenna gain that's simply given in dB. It needs to be given in dB in reference to something. Now we talk about polarization of an antenna, or polarization of radio waves. A radio wave is an electromagnetic wave, and it has an electric field and a magnetic field. And those two fields are always going to be at right angles or perpendicular to each other. The polarization is the orientation of the electric field, the E field only. In general, waves leaving a vertical antenna will have a vertical electric field, and waves leaving a horizontal antenna will have a horizontal electric field. Now, this by no means means that a wave from a vertical antenna is going to remain vertical, or that a radio wave from a horizontal antenna is going to continue to have horizontal polarization. The polarization is going to shift. Once the wave has traveled very far, the polarization, the E field, is going to start to move. Once it's reflected from the ionosphere, it's even worse. It can come down with what we call elliptical polarization. I guess it could come down with circular polarization, but most likely it's going to be more random. Circular polarization implies a uniformly rotating electric field. Things are not really uniform in nature. That's why you can receive, with a horizontal antenna, you can receive signals quite well that have been radiated from a vertical antenna. Once they have traveled through, to the ionosphere and been refracted. At VHF, when you're transmitting vertical to vertical, then it's important, because your vertical wave at VHF is probably going to remain more or less vertical for line of sight communications. But once you throw the ionosphere into the equation, then everything changes. Now we want to talk about ground effects due to polarization. Vertically polarized waves behave very differently than horizontal waves when they interact with the ground. A vertical and horizontal dipole act the same in free space, or far, far away from the ground. They have the same gain. But near the Earth, they have very different gains due to ground reflections. You get about 5 dB of free gain with a horizontal antenna when it's over real ground. You do not get that 5 dB of free gain with a vertical antenna that's mounted near the ground. So there's a big difference between vertical and horizontal polarization when you bring the ground into the calculation. Now I'm going to show you a plot of some antennas. The plot shows a vertical dipole and a horizontal dipole at 70 feet above ground. The horizontal dipole is uniformly 70 feet above the ground. The center of the vertical dipole is at 70 feet. So the dipole extends from over 100 feet high down to 37 feet. The gain of the horizontal dipole is 7.58 dBi. The gain of the vertical dipole, however, is 2.98 dBi. Okay, this plot shows the the pattern of the two antennas. The vertical antenna, as you might expect, radiates equally in all directions. And the horizontal antenna radiates mostly off the broadside. So we're actually focusing some of the energy that we are putting into the antenna. In the case of the horizontal antenna, we're taking it away from the ends and we're adding it to the broadside directions. Now the radiation angle. The radiation angle is the angle that your transmitted wave makes with the Earth. 90 degrees being straight up and 0 degrees being perfectly parallel to the Earth. The lower the angle, in general, the greater the potential skip distance. I say potential skip distance because even though you're striking the ionosphere at a very low angle, the ionosphere has to be strong enough to support the refraction of the electromagnetic wave. For a horizontal antenna, only the height above ground determines the radiation angle. Now, the radiation angle has to do with how far you're going to be able to get per hop. Now, we're assuming here that we're doing communication via the ionosphere. Now, as you look at the chart, this shows along the left-hand side axis, shows the wave angle in degrees. And across the bottom, it shows the single hop distance. Okay, I zoomed in a little bit so you can see it better. The radiation angle, for example, about halfway up the chart, you see a radiation angle of 10 degrees. If you come over to where it says E region, that would be the height of the E layer. And if you come over far enough and then come down, you can read the single hop E layer distance, which in this case, where the arrow says E region, if you come over there and come straight down, you see that you're looking at maybe 600 miles, 500, 600 miles for a wave angle of 10 degrees. And of course, the actual single hop distance varies with the height of the region. So the region is moving up and down from about maybe 62 miles to maybe 75 miles, something like that. If you come over further at 10 degrees, you will hit the F region. Now, the F region has a little bit wider range. It's somewhere between 130 miles to maybe 260 miles. So there's a big variation in your single hop F layer communications. So 10 degrees comes over, hits the F layer, and it looks like the minimum distance would be 1,500 miles. And if the F layer was really high, it looks like the maximum distance would be something like maybe 2,500 miles. Now, we've been talking about the radiation angle as if it was precisely 10 degrees. In general, no antenna is going to have a pinpoint angle for its takeoff angle. So what you're going to find is that, yeah, you can build an antenna whose maximum radiation is centered on 10 degrees. But there's also going to be radiation above and below 10 degrees. You might have your strongest signal at 10, but you're still going to have some signal going up at 5 degrees and some signal going up at 20 and 25 degrees. What this means is that your strongest signal is probably going to be at 10 degrees, at 1,500 miles, if the F layer is at its lower level. You will also receive signal further away and closer away than 1,500 miles. However, the signal strength may not be quite as strong because the antenna is not designed to have maximum radiation at any angle other than 10 degrees. Because this is a hypothetical antenna we're talking about. And when we start looking at antenna patterns, you will see that different antennas have different shapes of patterns. And when you start trying to figure out, well, what is an antenna good for, you have to think about where is its maximum radiation, how much does that radiation fall off at other angles, how high is the ionosphere, are we talking about F-layer communication, or are we trying to use the E region for communication? So there's a whole lot of factors here to be considered when you want to know what antenna to use or which antenna to design or how to design your antenna. Now we know that the height of the ionosphere plays a big part in how far you're going to be able to communicate, what your single hop distance is going to be. The height of the ionosphere varies with the time of day. It varies with the season, whether it's fall, winter, or spring, or summer. It varies with the 11-year sunspot cycle, it varies with solar activity. And of course, any time in the sunspot cycle, you can have a drastic change in solar activity. And there are still other unknown factors, either unknown because we haven't learned them yet or unknown because I haven't learned them yet, or unknown because we don't want to talk about them in this particular presentation. But basically, time of day, season, sunspot cycle, and solar activity are the major factors that determine the height of the ionosphere. Now I want to mention local skywave. Local skywave communication would require high angle radiation, probably 160, 80, or 40 meters. And now the polarization of the transmitting and receiving antennas do not need to be matched. In other words, you don't have to have vertical polarization to communicate with another station with vertical polarization. It doesn't make any difference when you're working skywave. A low horizontal dipole works great for local skywave, and low means 30 to 60 feet on 80 meters. Now, for long-distance communications, better known as DX, we want low-angle radiation. Again, the polarization does not matter. Anytime you're bouncing your signal off of the ionosphere, you do not have to worry about matching polarizations. In general, you want to use a horizontal antenna above 40 meters, a vertical antenna below 40 meters. On 40 meters, you want to use a horizontal antenna if you can get it over 35 or 40 feet. If you can't get a horizontal antenna over 35 or 40 feet high, then you're probably going to go to a vertical on 40 meters.